Hello and welcome back. So let's continue looking at vertical asymptotes. So again, a vertical asymptote is where our function is going to shoot off toward plus or minus infinity as we approach some line. So we want to find these, and vertical asymptotes are going to be where we're going to divide the function by 0, but only when p and q, as in the polynomial on top and the polynomial on bottom, do not have any common factors. So let's look at these guys here. So we'll start with f of x, and this is going to be x divided by x squared minus 1. So we need to make sure that we reduce this function as much as we can. So what I'm going to do, the top x, well, that's factored as much as I can. The bottom, x squared minus 1, I can factor x squared minus 1 into x plus 1 times x minus 1. And now this is as factored as I can make it. And on the top and the bottom, nothing cancels. So this is as reduced as I can make this fraction. So the top and the bottom don't have any common factors. And we can see that the bottom of the fraction, x plus 1 times x minus 1, this is going to be equal to 0 if, well, from this side, x plus 1 is equal to 0, or x minus 1 is equal to 0. So from this one, this is going to be x is equal to negative 1, or x is going to be equal to plus 1. So these are my vertical asymptotes. And we can see this if we were to graph this function. This function would look something like, if x is bigger than 1, we will be coming up. We have 1 there. If we are between, we'll do something like this. And this. So we can see that we have two vertical asymptotes here. Essentially, we're dividing by 0 in two places that don't cancel with the top. So this is how I would find my vertical asymptotes. Let's look at the next function. X minus 1 divided by x squared minus 1. The x squared minus 1 is the same on both of these. So let's look at this. So for g of x, we have x minus 1 over x squared minus 1. And we know that the bottom of this will factor. So we've got x minus 1 on top. Just going to put that in parentheses. And we'll have x minus 1 is x plus 1. Well, this simplifies. We can cancel the x minus 1 on the top of the bottom to get 1 over x plus 1. Now, I have to remember that I cancel this out. So for instance, I know that x cannot be equal to 1, and x cannot be equal to negative 1. Otherwise, I'm dividing by 0 in the original function. Even though they cancel out, my domain still doesn't have 1 and negative 1 in it. Now, what we'll notice is that here, if I plug in x is equal to negative 1, I'm dividing by 0, and it doesn't cancel with the top. So this is a vertical asymptote. X is equal to 1 is the other place that I'm dividing by 0, but when I've canceled my fraction, when I've simplified my fraction as much as I can, this is not a vertical asymptote. So ultimately, even though 1 and negative 1 were dividing by 0 in the original function, so they're not part of the domain, only one of them is a vertical asymptote because I have to cancel my entire function first. So when I draw this function, what's going to happen, we are going to get something that looks like this. We're going to have a vertical asymptote at -1. So here's our vertical asymptote at -1. And over here at 1, I have to be a little bit careful, because my function, I can't plug in 1 at that point. So the way that I might denote this is I'll have an open circle there, meaning I can plug in numbers next to it. I can plug in all these numbers here, I can plug in all these numbers here, but I can't plug in 1. I've got an empty circle, so I have to jump over that point. The very last function, h, I don't have a whole lot of room, but it'll be just enough. With h of x, we have x minus 1 over x squared plus 1. And here, the bottom of this polynomial is never equal to 0. If I take x squared plus 1, if I try to set that equal to 0, what will end up happening? I can move the -1 to the other side to get x squared is equal to -1. Well, no number squared is equal to -1 other than imaginary numbers. So there is no place where the bottom of this fraction will be equal to 0. So this has no vertical asymptotes. Essentially because I'm never dividing by 0 in this function. So that's pretty straightforward. And if we had vertical asymptotes, we can also have horizontal asymptotes. And horizontal asymptotes look roughly the same as vertical asymptotes, except they're lying on their side. So again, a line is a horizontal asymptote if our function is going to approach this horizontal line, specifically as x gets really big, either going to the right or going to the left. So we could flip all these pictures over and have duplicates where we're looking at it as x goes to the left. I've only drawn the ones as x goes to the right. And there's a few different ways that this could happen. One is that our function could be getting closer and closer and closer to this number, but it never crosses it. We could be coming from the bottom, or we could be coming from up above. Rational functions won't look like this, but this can happen with things that aren't rational. We can have an oscillating function that sort of goes up and down, and but the oscillations get smaller and smaller and smaller until we're pretty much right on this line. This is another way to have a horizontal asymptote. As we go further and further to the left, our function gets closer and closer to this line. And the last kind of silly way that you could have a horizontal asymptote is if your function is exactly that line. This is kind of silly, but again, this fits the description. Our function height is getting closer and closer to this line as x goes further and further to the right. It just doesn't have very far to go because it's already there. So again, horizontal asymptote, we're getting closer and closer to a line as we go further and further either to the right or further and further to the left. So how do we find horizontal asymptotes? This one is perhaps a little bit harder. There's just a little bit more to remember than with vertical asymptotes. So with vertical asymptotes, we're looking at where we divide by 0. Horizontal asymptotes, we have to look a little bit closer at the function. So a rational function is a polynomial divided by a polynomial. And the horizontal asymptotes, what we do is we look at the leading term in the top and the bottom, the numerator and the denominator. So here n is the degree of the numerator. It's the biggest power of x on top. M is going to be the biggest power of x on the bottom of the fraction. And if we know what n and m are, we can see what happens. If the top of the fraction is smaller than the bottom, as in the degree of the top of the fraction, n is smaller than m, then we know y equals 0, as in the x-axis itself, is a horizontal asymptote. If the degree of the top is equal to the degree of the bottom, then we have this funny number coming up. We look at the leading coefficient, a sub n, and we divide it by the leading coefficient on the bottom, which should be b sub m. This is the horizontal asymptote of the function. And then lastly, if the top of the fraction is bigger than the bottom, as in the degree n is bigger than the degree m, there's no horizontal asymptote. So there's three scenarios. So let's go through some examples where we look at these guys. So let's find the horizontal asymptotes, if they exist, of these three functions. So let's look at f of x. So we have 9x over 3x squared plus 1. For the moment, we're just looking for horizontal asymptotes. So what we need to do is find the degree of the top. So the degree on top. Here I have 9 times x. This is x to the first power. Anything by itself is just to the first power. So the degree on top is 1. The degree of the denominator is going to be 2. The largest power of x on the bottom of the fraction is 2. So the top has a smaller degree than the bottom. So 1 is less than 2. So we come back up to our chart. We go, the degree on top is less than the degree on the bottom. So y equals 0 is a horizontal asymptote. So y equals 0, is the horizontal asymptote. And if we graph this function, we will certainly notice that. So our function will look something like this, where if we go pretty far to the right, we're getting closer and closer to 0. If we go farther to the left, we get closer and closer to 0. Right in the middle, we sort of bounce down, come up, and then come back down. So there's a little bit of a wave in the middle, but for the most part, it's just going to be flat to the left and to the right. And let's look at the next one, g of x. Now we have 9x cubed over 3x squared plus 1. So the only thing that has changed is the top of the fraction. So let's look at g of x, which is going to be 9x cubed over 3x squared plus 1. So again, we just want to compare the degree of the top of the fraction to the degree on the bottom. Now the degree of the top of the fraction is going to be 3. 3 is the highest power of x, and 1 is the highest, 2. Yes, 2 is the highest power of x on the bottom, and 3 is now in fact greater than 2. So if we come back to our chart, the degree on top is greater than the degree on the bottom. No horizontal asymptotes. No horizontal asymptotes. Cool. And then let's look at the last function, 9x squared over 3x squared plus 1. Now the degree on top is 2, where the degree on bottom is also 2, and 2 is equal to 2. And when we have equal degrees, we have a little bit of work, but in this case, this is pretty easy. The horizontal asymptote is going to be y is equal to, we look at the leading coefficients, and it'll be 9 over 3, which is the same thing as 3.